Hey everybody, I'm Taylor Sparks again, and this is video 3 on how to make beautiful figures using Python. The first video was the basics of what are good figures versus bad figures. The second video was the basics of using Python to make fundamental, simple figures. This third video is the more advanced class on more challenging figures. So we're going to show you how to make figures that look kind of like these ones. Three-dimensional plots. How about this one where you do fill-betweens with lots of different data sets? This is just a generic figure we'll show you how to start with. Heat maps. We'll talk about multi-panel plots. Figures with multiple axes. So the regular y-axis and then separate y-axes with the same x-axes. Rietveld refinement using diffraction data. So these are some of the things we're going to dive into. Let's start with the simplest, which is just a generic figure. This is the one that I go to whenever I'm plotting anything. I just pull open this file and this is where I start with. So when we look at it, this code is already here. We're not going to type the code out together. Instead, I'm just going to go chunk by chunk through it and talk about what the chunks are doing. So we're going to grab the libraries, and you've seen this before. The only thing that we haven't talked about yet is the Seaborn library as SNS. That's going to give us colors, right? So that's what that is. We're going to grab our data. So the data is stored in the generic single file, singleplot.csv. This is available, so you can follow along if you want to. You can pull this up and try it for yourself. We're going to do that with pandas. We're going to read in that CSV into a data frame. Once we've got that data frame, that allows us to grab the different data sets, x1, well, x and y, x2, y2, x3, y3, because based off of the labels of those columns in that data frame. Okay, so we've grabbed our data. Now let's go ahead and grab some colors, right? I love the Seaborn rocket palette. I think these look great. And since we're dealing with 3 different data sets, I'm going to go to the rocket palette and ask it to give me 3 colors. So along the continuous color strain there, it's going to give us 3. One from the ends, one from the middle. Okay. If you wanted to, you could define your own colors. Like my postdoc advisor had this really great collection of colors that honestly look really good. And here's their hex numbers, and you can actually use those. I store them into a string so I could access the 0th index, the 1st, the 2nd, the 3rd, if I wanted to pull these colors out, and they look really good too. Okay, let's go ahead and make our plot. You've seen this before. Fig equals plt.figure. We're going to give it a fig size. We love square plots, so a nice 5 by 5 inch canvas to start with. Now on this, we're going to do semi-log plots. So semi-log, that means it's going to be logarithmic along the x-axis, but linear along the y. So we're going to go ahead and plot our 3 different data sets. Here we're plotting them with lines, right? We're doing markers that are different, triangles, squares, and circles. We're giving them labels. We are assigning them different colors from the rocket palette. We're making the inner colors white. Marker fill color is white. And we're giving them a size. So great. Let's go ahead and run this just as it is this far. So we're going to hit F9 on that section, and let's see how the plot looks. If that's all you do, it's not terrible, but we could do more. It needs a legend. It needs, I like the tick marks to be pointing in, right? Pointing in towards the plot from the top and bottom and the sides, and not pointing out. And then we need to add some labels and maybe mess with these a little bit. Like, I don't know if I like how it automatically chose the limits, so we can manually do all of that. Let's start with the ticks. We want it to go, the limits, we want it to plot from 1 to 10,000 on the x-axis. That's going to stretch it out a little bit more. And then on the y, we want it to go from -1/2 up to 16. Okay. Now, where do we want the ticks? You notice that by default, it puts them on the bottom and the left, but it didn't put them on the top or the right-hand side. Well, we can change that. We can manually say, all right, point them in, and on the right hand, have it set equal to true, and the top set equal to true. That's going to put ticks all the way around, right? We can change the label size, right? So that make sure that this is all 14. We can, yeah, so this is going to look good. And then we can put the label. We can choose where we want these labels. Right now you notice that the X label is labeled on the bottom, but if you wanted to, you could put the bottom and the top. I don't think you should. And if you wanted to, you could have it left and the right. I don't think you should. So we're just going to explicitly say that we only want it true on the bottom and true on the left. We don't want labels. We just want ticks, but not labels on the top and right. So we can set that. Now, where do we want the ticks to occur? Right now, by default, it's putting them every 2, right? What if that's too crowded for you? What if, like, for example, this separation between major tick marks is pretty big. What if we skipped a couple, right? What if we did it every 4? Well, we can do that. We're going to come over here. We're going to do y ticks is equal to numpy of a range. So remember, that creates a list of values from the start to the stop, not inclusive. So it's going to start at 0. It will not include 16.1. It'll go up to it. And it's going to go every 4. So it's going to give us ticks at 0, 4, 12, 16. Okay, so that's going to give us a list that we're going to use as our ticks instead of the default thing that it chose to do. We can tell it more info about the ticks. We can make sure that they're both pointing in, both the minor and the major ticks. We can make the major ticks 10 long and the minor 5. These are really small, the default values. Those are kind of hard to see. We're going to make those a little bit bigger. So let's, just with this portion of it, let's go ahead and run it again from the beginning and see how it changes things. When I run it now, you see, great. Right? We've got ticks going all the way around on all 4 sides of it. They're big enough that they're easy to see. This only now goes in increments of 4, which is better. And this goes from 1 all the way to 10,000. It's better, I think. So you can manually fit that to whatever you want it to be, but that's what I've got so far. Now the last thing we need to do is go ahead and put labels on the X and the Y axes, right? So for our X, we're going to label it particle radii, and it needs to be micrometers. So I'm going to turn on math font using the dollar signs and write \mu. That's going to give us the micro symbol, and then give us a Y label, and then tell it to plot a legend. So as simple as that, let's go ahead and run the whole thing now, and you can see that we are able to generate with this generic plotting file a lot of really great stuff and control it exactly how we want, and it looks terrific. Okay, last thing we did was plt.savefig. It's going to save it in the data for exercises folder within another folder called plotting. It's going to call this generic plot. Now there's other things here. It's going to we can set the resolution. I do DPI equals 300 and bbox_inches equals tight. That makes sure that it crops it just to where there's content, and it gives it high resolution, so you can use this in a figure for a paper. And that is what produces this beautiful figure, which is now ready for action. Okay, notice that it did the Greek letters and everything, so there's really nothing left to touch up on that. Okay, let's move to our next one. Okay, on this one we're going to show you how to do a plot where it fills in between the different lines. So this is the one that created this figure. It's the one where we're showing how resource production changes over time, right? As you go from 1998 to 2015, these different countries produced different amounts. So how do you produce this, right? Okay, we're going to start with the libraries, matplotlib and Seaborn, just colors and the ability to plot. Okay, we don't need pandas or anything because my student actually didn't know how to use pandas, and they brought in the data by hand, which is painful. This is why we learned how to do Python, so you don't have to do that. But they've got it, so we're going to use it. So we're going to create our figure, nice 5x5 square figure. And then over here, we have a list of all 22 countries that were in the list, right? In the order in which we're going to plot them, right? So here's all of our countries, okay? Now, we grab colors. This time I'm not going to use the rocket palette. I'm going to use Seaborn, but from Seaborn I'm going to grab the cube helix palette. And from that cube helix, that's the one that goes from this nice sort of greenish through blue. You can change it. Like for example, I've got mine starting at 0.5 for the start point. It goes through different bands of color. If I change that, you see now it goes from like this kind of teal through a purple. So toy around with this and figure out which one you like. I think it's good to start it at 0.5 with a rotation of -3/4. Just plug in different numbers here. You can read more about it at Seaborn, but I think it makes a nice palette. The point is we want 22 different colors, sequential, to represent these different countries. And the main ones we care about are the DRC and Zambia. Okay, we grab a list of all the years over which we're going to plot, which is 1998 all the way up to 2015. And then each one of these Y1 all the way down to Y22 represent the annual production of cobalt by these different countries. So Y1 would be Democratic Republic of Congo's production of cobalt for all these years. Okay, the next one would be Australia's production, and Botswana's, and so on and so forth. Okay, so to create this plot where we fill between them, we're going to do what's called a stack plot. So PLT, that's pyplot, and we're going to do the stack plot function. We have to give it the X value, which is the year. That's what we want on our X axis, and then we send it all the different Y values that we want to be stacked between them with colors. Okay. And then we label it, send it the labels, which is this string of countries. It has to be the same size as these that we've given it. And then the colors, it has to be the same size of all of the countries as well. That's it. That's pretty simple, right? Then we just tell it the limits, plot it from 1998 to 2015, from 0 to 100 on the y-axis, give it some labels, and it's as simple as that. That's what produces this. Now, something to be... you'll notice that I've got like Zambia written here, and I've got the Democratic Republic of Congo here, and I've got this vertical line and this thing rotated. How do you add that stuff? That's pretty easy to do. So to add the vertical line, we do it with the plt.axv line. So that's going to put a vertical line at some x location. So it only wants the x location. We're going to say at x equals 2003. That's when the war ended. We want it to be a dotted line. I think it makes it clear. And then black color. Great. You could change other things. If you want to change the thickness or whatever else, you could change it right in here. Here I wanted to label the Democratic Republic of Congo, so I went to 2006 and 10. So it goes to the year 2006, and then it goes up to 10, and it starts to label this here. Notice that I put this /n, and that forced it to do a second row. Instead of having this dangle off the map, off the plot, it makes a second row. Zambia, we changed the color to white, and we set it up here by plotting it 1999 and 92. So 1999, 92, and it plots it up there. And then this end of the Congo War, we were able to type that using this rotation equals 90. That rotated it 90 degrees up, so we got this nice rotated text. Then take a look at the legend. The legend was a little bit gnarlier, right? There was 22 different data sets, so we had to shrink it a little bit smaller so it would fit. And then you'll notice that Democratic Republic of Congo was actually our first data point, but we want it to match the colors on this plot, which is dark purple going towards lighter. If we didn't reverse this legend order, it would be light going dark going down. So we don't want that. So we can reverse it. We do that by grabbing the handles and the labels, right? Which is the handle is like this little block of color, and then the label is the one going with it. We're going to grab those from the current legends. We're going to go plt.gca and then get legend handles and labels. That's going to grab those and store them into these two things. It's a tuple, so it unpacks those into these two different variables. And then we're going to use those when we plot our legend. We're going to say, take this list and reverse it, reverse the handles, and take this list and reverse it, reverse the labels. And then we're telling it to plot it outside of the plot. We're using this bbox to anchor command. That allows it to plot it outside of the figure, which we want to do because we didn't want to cover all this up. That would be maybe not the right choice here. And again, I think that that's a little bit small. I think there's probably still things we could work on with this figure to make it more legible, but not a bad start. Okay, so that's how you do this fill between function. Let's go to our next one. Okay, let's talk about how you make multi-panel plots. Okay, so when I'm going to run this, we want to eventually be able to make a plot that looks like this, right? Maybe it has one set of data here, another one over here, and another one down there. How do you do this, right? Okay, well, let's start with the libraries. We're going to grab the same stuff as before, but a couple new things. From the matplotlib library, grid spec, we're going to grab grid spec. Okay, and then matplotlib itself, we're going to grab that so that we can change some things here. Right here, this first line, 2 lines of code, I put that in tons of my figures. What it does is it changes the font size universally. So the RC parameters, this is a dictionary entry, so this is the keyword for the dictionary, and this is going to be the value. We're setting the value in that dictionary for all the font size to be 14. That's just going to make the general font size to be 14 unless we say otherwise, okay? Then we're going to do PDF font type 42. That allows us to, if we want to, open this in Illustrator. We can save it as a PDF and then open it in Illustrator and modify it if you wanted to move things around by hand. Okay? All right, let's go ahead and grab our data. This is spectroscopy data for electrochromics. Electrochromics are cool in that they change color when you apply voltage to them. So we're going to see a change in transparency as a function of wavelength when you have it on versus off. So you have one data set over here for when it's on and one for when it's off. First off, you see that there's these 3 panels. I'm going to go ahead and delete it so it's just 2 panels first. And then we'll add it back in a moment. So I'm going to delete out that one of those panels. Okay, so let's say we started out with just a 2-panel plot, but you decided, well, first off, how do you make this 2-panel plot? And then how would you add that 3rd panel that you saw before? Let's go through the steps, okay? So we grab our data. On this one, it's kind of interesting. If you actually grab all of the data from it, it's actually really, really dense with data. This is what it looks like. These data points are right on top of each other. And maybe you don't like that. Maybe you like to be able to see the data points and make it a little clearer. You can actually downsample your data with this line of code here. So we're going to take the data frame, which we just read in from our CSV, and we're going to say that the data frame is now equal to the data frame before, but we're using the iloc, and we're saying grab every 10th row, grab the data point, right? So we're going to chop out we're only going to keep 1/10 of the data. If you do that, look how much it reduces this. It makes it much more, you can see that there's individual data points. You'll want to make sure that you say in the text that you did this so that they realize what you actually did. It's always important to say what you did if you modified your data in any way. But I think this is fine. You can say like, look, the data shown is actually downsampled by 1/10, and they'll understand that. I think it makes it a little bit clearer to see. Okay. We're going to grab the 6 different data sets, right? Here's from 30, 60, and 90 when it's turned on, and then 30, 60, and 90 when it was turned off. So you can see that the transparency as a function of wavelength changes. Here it's much more transparent, here it's much less transparent. So here's where we're grabbing those data sets. Again, we're reading them and we're doing drop NA so that we drop any empty columns or empty rows as we read them. I'm going to manually set the limits for the plots up top here. I'm going to say that X minimum and X maximum go from 400 to 800, so it's plotting from 400 to 800 on both of these plots. And from Y, it's plotting from 60 to 120, plotting from 60 to 120, okay? Just like before, we're going to grab some nice colors. You can use whatever you want to define yourself, or you can have Seaborn produce some nice ones. I'm going to use the Rocket palette again, but this time, since there's 6 data sets, we're going to go ahead and ask for 6 colors from the Rocket palette. And you see that it sequentially goes from this dark purple, lighter red, from red it turns orange, and it eventually turns pink. So it's this nice sequential series. I think looks good. Now we go ahead and prepare our multiple plot. So we're going to do, this looks just the same as before, this first line. But here it gets different. We're going to do GS equals gridspec.gridspec 4x4. So it's producing, instead of just one figure, it's chopping that up into a grid where you've got 4 rows and 4 columns that we can create figures in that sort of grid. I'll show you how to do that in a moment. And then it has this gs.update W space and H space. That's width spacing and height spacing. So for example, you see right now that there's this gap between these 2 figures. We can change that with the width spacing. What if we want it to be like a really big gap? Let's put 1 there, and it's going to put a big gap there, right? So it'll really separate these. Or if you wanted no gap at all, you could put 0 and they'll just butt right up to each other, and that maybe you want that. I tend to think that things look a little bit better with like a small gap. So I usually do like a 0.2 or 0.25, and I think they look pretty good. So you can clearly see it's 2 different sets of data, but it's obvious that you only need this one label over here. You don't need another label over here for this one because they line up nicely. Okay, that's my opinion. Do what you want. All right, let's generate this first panel over here. Okay, so when you do this, we have to create a subplot. So xtr underscore subplot is equal to our figure, which we created up here above, and then figure has a function called add subplot where it's going to create a subplot. And then where's it going to create it? It's going to create it using this grid spec, right? Grid spec, the 2 numbers represent the rows and then the columns. So we want it to occupy all 4 of the rows. Remember, it's a 4x4 grid, so we want it to use all 4 of these rows, but we only want it to go from 0 to 2 on columns. So it's only going to use half of our columns. That's going to make this figure, okay? Then you just plot your data. We're going to do plt.plot. Again, you've seen this before. It's just the X, the Y, it's whatever other values you want. We're giving it markers, we're giving it colors, you know, very straightforward. You've seen this before. We're going to give it ticks. I do this a couple ways. By default, this will create ticks from 0 until the maximum that you want it to go up to, divided by 4. So it'll do 4 ticks, right? On that one, what it ends up doing, it ends up creating 400, 600, 800, and then this one starts at 400, and the 400 and the 800 from those 2 different plots sort of pile up on each other, and it doesn't look good. So here, I chose to manually set where I want them to happen, and you can do that too. You can manually create where you want your X ticks and Y ticks to be. So here I say I want my X ticks to go from 100 up to 701 in increments of 200, right? Remember, if I had only gone to 700, it's going to get rid of that 700 there, right? Because it's not inclusive. It would go 100, 300, 500, but it won't include that 700, right? So I'm going to go to 701. And you don't have to start from 100. We could start from, right, in this one, we could start from like 300, and it's not going to look any different because it's off the map anyways, okay? So, and then for the Y, I want it to go from 60 to 121, 60 to 121 in increments of 20. So 20, 20, 20. So that's how I set my major ticks on this, and I just did it by hand because I thought it would look better that way. Okay, I'm going to tell it to turn on the minor ticks. I'm going to say information about these. I want my minor ticks to be length 5. My major ticks, I want them to be length 10. I want both minor and major to be all the way around, like left, right, top, and bottom, right, for major and minor ticks. And then you just tell it to plot them, right? Plot the X ticks and the Y ticks using the ranges that, in this case, we built by hand, okay? And then we tell it the limits, plot from 400 to 800, from 60 to 120. That's what this section of code is. We give it some labels. We tell it the transparency using Y label. Now, I do not use this plot X label for wavelength, because look what happens if I do. If I tell it to plot it as an X label, it moves it over here to the left. It's no longer centered, but really this wavelength corresponds to both of these data sets, and so I'd like it to be centered. You can make it center it. You can try and like move it over, but I find it's just easier to plot it by hand. So instead we're going to turn off the X label and I'm going to plot text. And I'm going to plot it at 650 and 52. So that's going to be X 650. So that's 700. It's going to start somewhere over here. And then it's going to start in Y at 52. So if that's 60, it's going to come down to 52. So when I run that, I find that it centers it pretty nicely. Takes a little bit of trial and error. Maybe you don't think that's quite right. Maybe you think it's supposed to be like 645. You can scooch it over just a hair and maybe that's better, right? But I think that's how I do a lot of these multi-panel plots, because I want this to correspond to both of those and it's easier just to type it myself. Okay, now let's go ahead and create the second panel. Okay, again, we're going to create another XTR subplot using fig.add_subplot using grid spec. And again, we want it to use all 4 of these, but we're only going to plot 2 of the columns at the end. So that's going to go from 2 to 4 over there. We grab our data just like before, except that we change the colors and change the labels to represent 30, 60, 90 clear as opposed to 30, 60, 90. We do the ticks and tick parameters the exactly same as before. Everything's the exact same, except you'll notice that I did not turn on my Y label. What would happen if I turned on my Y label for this other multi-panel, right? If I turn this on, look what it's going to do. It's going to put that Y label right there, and that just looks ugly. We don't want that. So we're just going to turn it off because it's obvious from this that it corresponds to both. So when I run it, you can see that this transparency percent is clearly acting on both of these. We don't need the tick labels. We don't need the Y labels. Okay. Now, what if you wanted to do like we had it initially and have like a small box here and another small box here? How would you further modify this? Well, easy enough. Let's go ahead and grab this whole second panel, right? This whole second panel here. And we're going to copy it, and let's make a third panel, okay? So I'm going to call this generate third panel, okay? Up here, let's go to our second panel and change things. Instead of it plotting all 4 rows coming all the way down 4, let's have it just plot the first 2. So instead of 0 to 4, let's have it go from 0 to 2. The third one, obviously, we have to do the opposite. This one has to go from 2 to 4. Okay, now let's run that. And when we run that, yeah, there you go. We've created this figure and we basically plotted it twice, but once on this smaller grid and once on this smaller grid. Now, what's wrong with this? There's lots of things that are wrong with it. These numbers don't need to be there right there. So let's go to panel 2, right, and turn those off. So we're going to go to our labels. Right now, this is panel 2. The label bottom is set to true. Let's set that equal to false. Like, we don't need that there, right? But what we do need, it's not really obvious that this 60 to 120 is the same thing that goes 60 to 120 there. That may not be obvious, so maybe we need to turn on those labels for the y-axis. Let's turn them on the right-hand side by setting this equal to true, and we'll do that for both panel 2 and panel 3. So I'm going to come down here to panel 3, and I'm going to say plot those on the far right-hand side. Yeah, so now you can see pretty clearly that this goes from 60 to 120, 60 to 120. I think that this is a pretty intelligible graph at this point. So you could divide it up however you want. Here we did a square grid, which was 4 rows by 4 columns, but you could do whatever you want. In fact, in some of the videos I'm gonna, as this video goes on, I'll show you other examples where it's very different, 3 by 15 or whatever, and that's no problem. Okay, so that is how you do multi-panel plotting. Really, really powerful tool. One of the main reasons why I plot things in Python. Okay, let's go to our next one. Okay, let's talk about how to make a heat map. Heat maps are really cool. They're a great way to show 3-dimensional data in a compact way. So in a heat map, you plot not only X and Y, but you plot Z as color, right? And so you can see in this one, for example, with diffraction, how things change, right? The lattice parameters change because the peak positions shift as we increase the pressure. They change, right? So how do you go about creating this? Okay, here's our libraries. We're going to grab everything we did before, NumPy, PyPlot, Seaborn, Pandas, GridSpec, and then we're going to grab this colors thing, and I'll show you that in a moment. Okay. Again, I'm going to set my universal font to be 14 for everywhere here. We're going to grab our heat map data. If you look at where this data came from, let's go ahead and grab it in our data for exercises folder. If you look at heat map data, this is how it was organized when my grad student gave it to me. So you've got this first column over here representing Q. Q's, think of it kind of like 2 theta. If you're not familiar with Q, you know that in diffraction you plot the intensity against 2 theta. Q you get from 2 theta. It's a transformation of it. So think of it like the position of the peak. And then here's all the intensities for the different pressures, right? So you've got 1 different pressures and all of their intensities associated with them. Okay, so this is one way to organize the data. The problem is that when you plot a heat map in Python using Seaborn, what it wants is 3 columns. It wants a column representing X, Y, and intensity, right? So we need to transform this data into 3 columns. What we would like if I go ahead and insert this, what we want is a column representing pressure and a column representing intensity, and then Q. So pressure, if this first pressure is at, let's say, like 13 gigapascals, we want it to be 13 for every single one in that series. For all the ones where it's Q is with for all of these Q values, which go, there's thousands, and it's like 6,000 in a single data set, right? A single data set goes, there's 6,782 entries in a single data set. So we need to repeat that 13 all the way down to here. And then we need to go to our next pressure. Maybe it was 14 gigapascals. And we need to repeat it another 6,700 times. So that's tricky. And then we need to take all these intensity values, right? We need to grab these intensity values. This guy all the way to the bottom. We need to grab him. And we need to move these over to this column, and then we need to grab the next one all the way down, and we need to put it underneath it, right? So this is tricky. This is some data manipulation, but we can do that, and Python is a great tool for doing it. So I'm going to not save this, and I'm going to exit out. And let me show you how I went about manipulating that data, okay? Well, first thing I did is I grabbed that data from the comma separated value sheet using pandas, and I stored it in a data frame. Then my grad student told me, hey, even though we ran Q from, 6,000 or 6,700 data points, technically we only want to grab from 504 to 4,066, or Q values from 2.25 up to 4, because that's where these all are in common. Sometimes we only measured 2.25 to 4, so some of these might go a little bit further out in another direction, but we only want to grab the block where they're all comparable. Otherwise you'd have missing spots in your heat map. We don't want that. So great, we can do that. We can grab the Q values by going to the data frame in the Q column and grabbing it using the loc function, the rows 504 to 4066. We're going to drop NA, and we're going to convert that to a NumPy array, because the Seaborn heat map wants it to be a matrix, right, of NumPy arrays. No problem. So we're going to do that, and we're going to grab all the different pressures. All these different Y1 through Y21 represent different pressures, right? So all the intensities at different pressures. Okay, so we're grabbing all those intensities, we're grabbing all that data. Okay, now we need to take that data and turn it into 3 columns. So the first column needs to be Q. Q needs to have that same range of, incremental values of changes in Q, right? All this tiny resolution moving down, it's thousands of data points. We need to be that Q value repeated 21 times in a row for the 21 different pressures that we measured. Great, we can do that. We're going to say, all right, for Q in range of 21, that means it's going to be a for loop that goes through 21 times. It's going to take Q, which started out as an empty list, and it's going to append to Q this X1 value, which is just our Q value. It's going to repeat that 21 times. It stores that as Q. It adds to Q over and over. So by the time we run this, let's go ahead and run this first section. When we run it and we open up Q, Q is something, again, it's going to be thousands long, but it starts out with 2.25, and then it increases up till 4. You can see it get very close to 4, and then it starts over again. And it does that 21 times. As I scroll down, it does that 21 different times, okay? For the 21 different pressures that were investigated in this study. Awesome. Now let's move on to the next one. For pressure, here's the 21 different pressures that they had, okay? Our 21 different pressures. We need to start out making a list of those, so we do that. Now we create a new list, which is empty, called new pressures. And for each pressure in our pressure list, like we're going to start out with this first one, we're going to create a new NumPy array filled with that value. And it has to be as many long as we want in as many Qs as we're going to consider, which turns out to be 3,563, right? So it's going to put that same pressure all those times to label that those are all part of the same pressure group, right? Then we have to take our intensities. That's easy. We just take all these individual intensities corresponding to the different pressures, and we concatenate them together. That just stacks them up. Okay? Sweet. Now we've got our 3 columns. So we've got Q, pressure, and intensity. So we have 3 things. Here I go ahead and I scale intensity down so that the color map can more easily tell the highs versus lows. That's common in X-ray diffraction, is that they'll scale it by 1/2 or a logarithm. Okay, I'm going to say that my results, that's what we're going to plot, it's a new variable called results, is the NumPy transpose of the vertical stack of Q, pressure, and intensity. Okay, so it's taking those individual arrays and making a matrix out of them is what that's doing. Now, we go ahead and say that the data set is equal to, we're creating the dictionary. We're saying that Q is this, pressure and GPA corresponds to pressure, intensity is intensity. We're going to use those for labels on the plot. And then we come over here, we're going to reset the index and do pivot table, telling it, okay, plot it with the index as Q, with the columns as pressure, and for the intensity, that's going to be the heat map, we want to use intensity. Okay, so you're basically explicitly telling it which one of those you want to be in the heat map. Then you go ahead and make your figure, use grid spec. So in the figure, that basically is what we need to do to be able to create this middle panel. But you'll notice that I think a really good way to do heat maps is to not just show this middle region, but to show what the individual data set on the far left and the far right ought to look like. So here's the one on the far left, the one at the lowest pressure and one at the highest pressure. So this is technically going to be a multi-panel plot. You've got one panel over here, one middle panel, and then a right panel. So let's go ahead and do that. We're going to create our figure. We're going to do grid spec. I'm going to call this a 4x6 plot. So 4 rows, 6 columns. That allows us to do 1 column here, 4 in the middle, and then 1 column at the end. Okay, that's what the 6 columns are going to do. Here's the spacing. I put really small horizontal spacing between these. Okay, but you could make that larger if you wanted. If you wanted like a great big spacing, you could move that and make it bigger. I thought it looked better with a really small spacing on this one, so I might keep that small. Maybe we'll do like just 0.1. Okay. All right, now let's go ahead and fill data in our first column on the left here. Okay, so this is not a heat map over here. That's a scatter plot. You can see that as the intensity changes, the color changes. Okay, so we're going to do XTR subplot, fig add subplot. We're going to do our grid spec. We're going to take all 4 rows. We're going to use all 4 rows here, but we're only going to go from 0 to 1, this first column. Great. Now, this original colors, if you tell it to do a scatter plot and you just give it the data in there, it's going to take the maximum of the color range. It's going to be like a bright yellow, like this brightest yellow here will be there. But you can see that actually in this first data set, that's the brightest to get. It's less bright than one of the later data sets. And on this one over here, this brightness, even though it's the maximum for this highest pressure, it's less intense than it was in the middle. So what I needed to do was manually change my color maps on these end members to more closely match that from the heat map. So we wrote, well actually I had the internet write for me. I found this on Stack Exchange, a way to truncate your color map where you don't look at the entire section of it. I'm going to skip this for now. You can look at how I did it. I'm not going to bother explaining it though. Basically, we started out with the Rocket color palette and we only went from 1/10 to 55% of it. That's what you're seeing here, as opposed to going from 0 to 100% of the color map. We only did part of it so that it more closely matched the heat map. That's all I'm going to say about that. Okay, we did a scatter plot. We sent it check this out. I'm calling this Y1 and X1. That's because I've got this thing rotated on its side, right? The X1 is actually now going to be the Y value, and the Y1 is going to be the X value. The size I set equal to 1. The color I set equal to the Y1 intensity, right? And then I gave it our new color map, okay? So I did not give it an X label. We didn't need an X label over here. That's just intensity. I didn't give it any tick marks. For the Y label, I told it that it was in Q space, which is 2 pi divided by D, the interplanar spacing, which has inverse angstroms spacing. So you can do that. And then I labeled that this was the pressure corresponding to 13.06 gigapascals, right? So that's how we went ahead and got this plot. How did I make it plot in this funny way where it's plotted backwards? Well, I plotted it on the Y limit from 4 to 2.25. That's why it's going from small numbers to high numbers here. You just tell it. You can tell it how you want it to plot. I told it I want it to start at 4 and go to 2.25. So I plotted it backwards from what you would normally do. But that allows us to line up this peak here with that peak there, this peak with that peak, right? It lines up nicely, okay? Okay, so I plotted it with the correct limits. I put the right ticks on it. I want it to go from 2.5 in increments of 1/2 so you can see it clearly. And then I want it to turn on the left and the right tick marks, but not the top and the bottom. So we were able to do that. Pretty straightforward. Okay, so that's our left wing. Now let's do this right wing over here. The right wing panel, the one on the far right, is going to be the exact same. Check it out. We're going to do XTR subplot, fig add subplots. We're going to use all 4 rows, right? We're going to use this whole region top to bottom, but we're only going to go from columns 5 to 6, right, over here, right? We're going to do a scatter plot again using our new color map so that it matches the heat map. By the way, what would it look like if you didn't do that? Like, what if I didn't do new map? Let me show you what the problem is. If I just put in rocket here, if I tell it to use the rocket map, take a look at this. It's going to take the top of that peak value and make it as bright white as possible. But we know that that bright white does not, that's not what's actually here. The bright white is reserved for these. These were the highest intensity in the actual whole data series. But you didn't know that when it did a scatter plot, it just took the maximum value in the data that was given in this series, right, in this one pressure, but in the whole data series, that wasn't the highest. That's why we had to map it over to this new CMap. So that's why we did this change where we reduced it. And that made it look much more closely like it ought to. Like, that was just starting to turn purple, and there you see it's matching. This is just turning red, and it's just turning red there. So it was a much closer map. Granted, I just eyeballed that, but I think it made it easier to interpret this. Okay? All right, on this one, I didn't need any labels, so I just turned them off. Didn't need any tick marks, tick labels, just tick marks. So we just turned on the tick marks. And then again, I told it that this corresponded to 43 gigapascals. So pretty straightforward stuff you've seen. Now about the heat map, right? So in this middle one, we're going to do XTR subplot, and we're going to do it. We're going to plot from columns 1 through column 5. That's going to give us this big section in the middle for the heat map to be. And then the heat map itself is pretty simple. You just go fig equals SNS, that's seaborne, dot heat map. You send it the data set, right? We already packaged up that data set up here. Up here, we already, where was it? Right here. Here's where we defined our data set with, we told it what the index, the columns, and the value for the intensity should be. Great. So it's ready to go. We told it to turn off the tick labels. We didn't want any tick labels. And on the y-axis and the x tick labels, we just gave it 4 of the data sets, and we gave them the data points, and I manually told them when to insert those on the 0th index, 7th, 13th, and 20th data set, and that's it. And then we're ready to save it. So that's one way to do it. There are other ways you can do IM show. So I'm going to put these are commented out. These will also produce nice color maps, but I think that this does a pretty slick job, and I think it's the right way to do heat maps where you show the end members on the sides like this, so you can really see what's happening in higher resolution than just the heat map would tell you alone. Okay, so that is how you do heat maps. Let's move to our next one. Okay, this one's pretty gnarly. This is multiple axes. What do I mean by multiple axes? With multiple axes, I mean that when you plot it, you've got your x and y, but maybe you want like a y2 shown in red and a y3 shown in light blue. All 3 of these y's, right? This capacity, Coulombic efficiency, and discharge energy density, those are 3 different variables, but they all correlate to the same x variable, which is cycle number. So for batteries, when you cycle the battery, cycle number is really important, but there's lots of other parameters, right? Capacity, efficiency, discharge energy density. Those are all a function of cycles. So how do you create a plot like this? It's pretty tough. So here's how you go. So we're going to bring in the same libraries plus this multiple locator from matplot.ticker. That allows us to do different tick marks for these. We're going to use that in a minute. First off, I'm going to set everything to be size 14 font. We're going to grab our data, which is stored in this multiple axes Excel file. You can see it yourself how it works. I read it instead of as a CSV, this time we read it as an Excel sheet. Right, so that's fine. When you read it as an Excel sheet, now you've got different worksheets in there. So you have to go sheet by sheet for the sheet in the sheets of our data frame sheet. We're gonna read this in, right? So that brings each of those in and stores it into this data frame. No problem. So now in our data frame, we grab the different values, right? So we've got the one with cycling 100 times, cycling 20 times, the capacity, the efficiency, the discharge energy density. So we're grabbing all these different values and storing them into these variables here. Nothing too crazy so far. Let's grab some colors. Here we used ROM's colors. Okay. All right. We had to build a custom function here. And I say we. This is all my grad student Kai, who's brilliant. When you do these, like, see how there's this other axis over here, but we're only like showing the far right hand one. The other, like the horizontal bar going out to that, has been made invisible. He wrote a function to do that where you send it a set of axes, whether it's the regular y-axis, the y2, or this y3, right? It creates them invisible, and then we just turn on just the far right-hand side afterwards. So he wrote a function to do that over and over for us. Okay. Now here's where it gets very different than what we've seen before. Instead of just doing figure equals plt.subplots, we do figure comma host. So the figure is now going to have its regular host axis. That's the typical x and y. Okay. In addition to that, we can have twin x. So we're going to come down here and see how we're going to take our host, which is our normal y-axis, and we're going to twin it, meaning we're going to create a second y-axis that uses the same x values but as a duplicate y-axis. So it's called twin x is the function. So we're going to call that par1, right? So par1 is this red axis. Par2 is we're going to do it again, and that's going to create this blue axis over here, okay? So we're making twins of this x and y axis setup, okay? And then we can offset them, like we moved its position over, like this light blue one. The red one was fine, we just put it on the right hand side. But this one, we moved it over off a little bit, okay? All right, what else can we do here? So he uses his function that he wrote, this make patch spines invisible, and he sends it par1 and par2. Here he sends it par2, basically turning off the grid, right? Turning off all of the box, like you can see that this normal black box is there. He's turning that off, and then he's just going to manually turn on the right-hand side. He's going to turn on this blue section on this far right-hand side for that par2, making the rest of it invisible. So some slick work there. Now he goes ahead and he plots his data. On the host data set, he's plotting some data. On par1, he's plotting different data. On par2, he's plotting other data, right? They all have the same, well, yeah, you're using the same approach here. It's still like before we saw plt.plot. Here it's not plt.plot, it's host.plot or par1.plot, because you're being specific about where you want these to plot according to which y-axis, okay? Giving them the markers that he's chosen, the line styles, the marker face color. Here they did some alpha, meaning transparency, so that you can see that these are like piled up on each other. That allows you to actually see through them to the ones underneath, okay? For each one of these three y-axes, you need to set axis limits independently, plus your x-axis. So there's 4 of them, right? We're going to set our x to go from 0 to 100 cycles. We're going to set our first y-axis to go from 0 to 1200, 0 to 1200. We're going to set our next one to go from 0 to 105. Our third one to go from 300 to 1800, right? We set these independently by doing host.setXlim as opposed to, say, par1.setYlim, par2.setYlim, okay? We can do the same thing with the labels. We need to create 4 different labels, one for here, one for there, and one for here, and one for there. So we set our 4 different labels, okay? We can change the colors of those different labels. Here we're doing that. We're changing the colors of them. We can change the tick, like the major tick mark separations. Here they're separated every 200, but here they're separated every 20, and here they're separated every 200, right? So you can change different tick marks. So here we're doing that for the host, for par1, and for par2, and for the x-axis, right? So it's a little gnarly, but you can do it. You've got this as a guide if you want to that I've made for you. And then the tick parameters, we're telling it how long we want the tick parameters to be. Then the last thing is these different data sets were plotted on different hosts. Like one was on the host and one was on par1 and par2. So if we plotted legends, that's a problem because they weren't all part of the same figure. We'd split them into sort of like 3 figures in one. So what we needed to do is grab all the information from those different plots that we created, which were up here. Like these were the plots that we created when we plotted them. And from those, we're going to get the labels for L and line. So for each one of these data plots, we're going to grab the labels that were there, right? And we're going to use those to now plot the labels in our legend on just one of them. On just the host plot, we're going to plot all of the plots, even though they were technically plotted on par1 and par2. See what we did there? So that allows us to have just one legend here with all that information. Now in this one, something that bugged me is I was never able to get this far right-hand line to turn red and this far one to turn light blue. So I didn't want to fight with it anymore, so instead I exported it as a .eps, and that means that it's vector file, and we can open it up in Illustrator, and I could go ahead and manually change those things. So if you come over here to where it got saved, under data and then plotting, this is now something that I could open in Illustrator, and I could just manually make that one change to make that one line red and the other one blue, light blue. Okay, so that's how you go about making these really kind of gnarly multi-axes plots. Okay, let's go on to our next one. Okay, just 2 left. Let's do Rietveld first. If you are a material scientist, very likely you're familiar with Rietveld refinement. It has to do with X-ray diffraction, right? When you plot X-ray diffraction, you've got intensity versus 2 theta, but it's very common for you then to say, okay, here's what I think my phase is. What would its pattern look like, and how well does that match the observed pattern? So the experimental data are shown in blue data points here, and then we have our simulated pattern with this orange color, and these are simulated where we expect the peaks to be for these given phases. And then you can even include like, oh, and plus the background sample holder is this light blue. And then you take the difference. You take the blue points minus the yellow points, and you get this difference curve. And if you match it really well, then you did a good job of figuring out what your phases were. So if you haven't heard of this before, don't worry about it. It's a whole field. There's great software packages out there in my tutorials. I'll probably put a link to one of them in the description below. But making, like, the output is a lot of information. It's the real data, it's the fit, it's the difference, it's the sample holder, it's where you expected the peaks to be for different phases. These are complicated figures. So I think that this is a beautiful way to present them. It's dense with information, and it just gives you what you need to know. So how do you make a figure like this? You just use this file exactly as. When you run your Rietveld refinement, it will spit out something called, your final report is going to have all this information. And I made it really simple so that all you had to do was export it, and then I would read it. Like, it will come with these names already there. And so you just run this Python script and it will create that figure for you just like that, which is really great. So you've got your X value, that's your 2 theta values. You've got your observed data points, your fit, the background, and then the HKL positions for the different phases that you refine. Now here I only did 2 phases in my refinement. If you did 22, it would just keep on giving you more columns, and you could just keep on reading them in. That would be no problem. So that's what PyGSAS2, the Rietveld refinement software, will spit out. How do you use that? Pretty straightforward. We're going to grab the same libraries as before. We're going to set the font and the PDF so that it's editable in case we want to tweak this in Illustrator afterwards. We're going to read that file in. It's a CSV, so we're going to use pandas to read it in. We're going to then go to our data frame where we read it in, and we're going to individually grab the X data, the observed data points, the Rietveld refinement, the background, and the HKL positions for your 2 different phases. Okay? I'm going to set the limits of my plot. We want to plot from 15 to 100. It's pretty common. 10 to 90 is also pretty common. We're going to use some colors. Here I think Rom's colors look great. That blue and the the pumpkin and the cerulean and Neptune, his colors, they look really good, so we're going to use them. We're going to make a multi-panel plot. There's this one big panel where most of the action's happening, but you've also got these really small panels up here corresponding to the phases and where you expect to see peaks. Like this yellow peak comes from a phase. Now you know that comes from this cobalt 304 phase and not cobalt oxide, because we put these histogram tick marks. That's really helpful. Like this really big yellow peak, it comes from the COO phase, the rock salt phase, as opposed to the spinel phase. Okay, so that's why we do those. So we're going to do a multi-panel plot. We're going to do it with grid spec, and we're going to do 15 different rows, right? So that the first row 1 and row 2 can be for these histograms, and all the other 13 can be for the main figure, right? You can divide it however you want, but that's how I do it. With small spacings between them, right? Little spacings there. All right, so let's make this main figure first, this big one. So we're gonna do the same as before. XTR subplot fig equals add underscore subplot. We're gonna use grid spec. We're gonna go from rows 2 to 15. We're gonna leave rows from 0 to 2 for making these little histograms up top. We plot the data. We're going to plot X data and the Y observed. We're going to call it the experimental data. Because it's experimental data, I like to use an actual marker. That's why you're seeing these little blue markers here. I didn't do a fill color because I think it's kind of nice to be able to see how those like line up on top of each other. And then for the fit, we don't use markers, but we do a line, and we give it this color, and we give it this nice label telling it that we achieved a 5% weighted residual. Same thing with the background. We don't use markers, we use a line. So that's what this light blue is. And then the difference, check it out. I never actually defined the difference as a data set. I just do Y fit minus Y observed. That is the difference, right? So that's this gray data set down here at the bottom. Great, we've got all of our data there. Now we need to add the other stuff, tick labels, legend. You've seen all this before. We manually have it tick every 20 on here. I don't put tick labels on the y-axis because it's arbitrary units, so we don't need to. So I put ticks, I just don't put tick labels. Right now it's ticking every 2,000 intensity units. I just don't care what those are, so I don't label them. I turn on my tick on all four sides. We give it X and Y labels. We've seen this already. Give it a font size for the legend. I had to make this a little bit smaller than I would normally do to make this fit. That's the name of the game here. And then I actually plotted text on here to say, hey, these two phases are present. It's 60% rock salt, 40% spinel. Okay. Now, how do we make these upper sections? So here we're going to add the subplot for phase 1. This is pretty cool. So we're going to plot from row 0 to row 1. So it's going to be just this top sliver. Okay. And then here's how it works. So the different phases, when you run your Rietveld refinement, you don't know how many HKLs are going to be present. It could be 30, it could be 5, right? It could be any number, right? And so here's what we do, is we know that those are stored in this variable HKL1. If I come over here and I look at HKL1, here's where they're stored. So what I want to be able to do is I want to go through this and item by item plot each one of them until there are no more. That way, HKL1 and HKL2, even though they're very different numbers, I use the same exact approach for both. So for HKL1, I'm going to say for XC in HKL1.value, so it's going to go value by value in that list, and we're calling it XC. It's going to plot a vertical line, AXV line, at X equals that position, and it's going to give it a color. That's it. And then you can turn on, you can do your tick parameters and the limits and all that jazz just like before to create this little mini plot. Here I don't want any tick marks. I just want the vertical lines there, and I do want to plot off to the side the name of that phase, Cobalt 304. And then I do the exact same thing for my second phase here. I'm going to go value by value in my HKL2 value list and plot little gray lines so that you can tell where they line up. So again, I think this is just a terrific way to make a complicated plot, but one that is much better than the standard, like you don't want to print the screen from your Rietveld refinement software. This is the right way to show it, I think. Okay, so that's this one. Let's do one last one and then we're done. Okay, let's talk a little bit about plotting 3D. This comes from a really great tutorial I found on this guy's GitHub page on Data Science Handbook. It's actually taken from a textbook. In this same family here, this same family of books are really, really great. So it's taken from there. I've put the reference up top so you can check it out. And this is available under a Creative Commons license. So credit to them for making this available. I think it's good stuff. So the libraries we're going to bring in, from MPL Toolkits, we're going to import mplot3D. And that's going to allow us to make these 3D plots. Okay, let's get started. So let's start with just a basic 3D scatter plot. So we're going to declare our figure. Figure equals PLT figure. We didn't do the sizes here because I took it straight from their code. So I didn't make it square or whatever. We're going to say that its projection is a 3D figure, okay? So let's get the data we want to plot. We need to have three-dimensional data, so we need X, Y, and Z. So for the Z, they do NumPy lin space, so that's going to linearly space the data from 0 to 15, and it's going to do 1,000 values, right? So it's going to produce 1,000 values linear space 0 and 15. It then takes those values, and for the X and the Y data, it just runs those through sine and cosine. Okay, so that is now going to be our X, Y, and Z data. So plotting is as simple as this. You just plot AX, that's our axes, right? Where they define the axes here, dot plot 3D, where you send it X, Y, and Z, and then they tell it to plot it in gray. So let's go ahead and run this first cell. By the way, this is a cell. You see how I did this number, this pound sign space percentage. That allows you to hit Control Enter, and it will just run what's in this cell, which is kind of nice to do. So now it went ahead and it created a plot. Sure enough, it plotted, I ran this other stuff. This first part that we've gone through so far would have just produced the gray line that did this like sort of spring shape there. Now, how do they get these other data points? Well, they go through and they say that Z data is equal to 15 multiplied by a random number, where they produce 100 random numbers between 0 and 1, multiply those by 15. So now you've got 100 data points, which are somewhere between 0 and 15 for your Z. And then they run those through sine and cosine, and then they add a little bit of noise. They add a small random number to each of those, and that's what these data points represent. Now, they did a scatter 3D, and remember, scatter plots encode 4 information. You've got the X, Y, this time Z, so it's going to be 5 information. It's got X, Y, Z, and then marker size and marker color. So here they don't give it size, so they're all going to be the same size, but it does give it a color. It says for color, use the Z data, right? So as it goes from low Z to high Z, you'll notice it's also changing color as it moves vertically. So a really cool way to do it, and the color palette here is nice, this winter in reverse color palette, okay? What about contour and surface plots? Here's another way to do it. What if you wanted to make a plot that looked like this? This is another type of 3D plot. Okay, here's how you do it. they defined a function where when you feed it x and y, it's going to return the sine. Let's see, it's doing sine of the square root of x and y squared and added together. So it's some custom math function that has this sort of shape. That's what they've created here. So they start by creating lists for x and y, so their data for x and y. They do linear space from -6 to +6, 30 values. They then take those and they create a mesh grid. So this is a NumPy function, NumPy mesh grid. It basically fills out the space between those. You gave it x, you gave it y. It creates a grid in that Cartesian space. Okay. Then they send those values to the function to create the z value. Okay. And then they plot it. So they come over here, they tell it that the projection is 3D. Here they're doing plot surface, where they send it the x, y, and z values. This is R stride and C stride. That's the step size in the columns and the rows. They give it a color palette, viridis, and they say no edge color, and that's what produced this beautiful shape here. Then they labeled it X, Y, and Z, and they gave it a view angle. Like if you wanted to view it right along a 45, you could. Now we're looking right along that 45 there, or you can move it back to whatever you wanted to view this by. If you wanted to tilt it down a little bit so it's not so tilted up, you could tilt it way down. So you could look more kind of right at it that way. You can change, you can play with that view angle a little bit. That's one way to do it. Another way to plot this would be here. I'm going to uncomment this. Would be to plot, let me just run this now, is to plot it as contour lines. So if you look at topographical maps, it produces these contour lines. Let's look down on it. Let's look straight down on it, actually. If we look straight down on it, this will now look like a topographical map. Oh, oops, we want to just run this section. F9 on that section. Yeah, and sure enough, there's our topographical map of just that region, which is pretty cool. So that is a bunch of plots, and I'm sure that there's others. You can drop a comment below if there was a type of plot that we didn't produce here today and you'd like to know how to go about doing it, and I'm able to. I'm happy to show you how we would go about doing that. I think it's worth the time because you can make some really complex but beautiful plots with this type of software. So thanks for joining me as we talk about plotting, and we'll move on to our next video.